Hello everyone, welcome back to my YouTube channel. In this video, we'll discuss about maximum power transfer theorem and the proof when load resistance is the same as source resistance or else RS. First, you should know the statement in this theorem states that in any active network, maximum power delivered to the load takes place when load impedance ZL equals to the complex conjugate of network impedance, that is Z equivalent or simply Z. So the maximum power transfer theorem, whatever the circuit they are given, you need to rewrite that circuit in the form of Thevenin's network, where it consists of a AC circuit, VTH as a source with respect to ZTH or Z equivalent, and the load is connected across the terminals A and B, and it says that the load impedance is same as complex conjugate of equivalent impedance. So Z equivalent means obviously it is having a resistor and reactance, so that it has two cases. In the case 1, when the load is pure resistive, means that if we're having this rewriting the circuit diagram, Z equivalent I can rewrite that as R and JX. I'm considering this as RL series load or else RL series circuit, whereas it consists of R and JX. This is connected across the terminal A and B with respect to the load RL. It is a pure resistive load, that's why it is RL. If it is just a AC circuit, it will be ZL. So that now you write the total impedance, that is a series, it is total impedance is R plus JX plus RL, so that you can write as Z equivalent plus RL, that is nothing but R plus JX plus RL. And the total current I is given by, according to Ohm's law, or else I is given by V divided by Z. So V is nothing but VTH. So here Z is nothing but Z equivalent plus RL. Therefore, VTH divided by R plus RL, real terms I am writing R plus RL plus JX. So if I want to write magnitude of this, means a square root of VTH divided by R plus RL square plus X square, it will remove the J terminal. So that you can rewrite that as this is VTH square. You can rewrite this as square root of VTH square is nothing but VTH, and in a denominator square root of R plus RL whole square plus X square. So this is when the load is pure resistive. So that now we'll define power delivered to the load. So the power delivered to the load, which is given by I square into RL. Just now we have know the value of I, that is nothing but VTH divided by square root of R plus RL square plus X square. Therefore P is given by VTH square, I square it is VTH square divided by, so if we are squaring this, means this will be square and square root and square will get cancelled, so that you can get VTH square divided by R plus RL whole square plus X square into RL. Okay, therefore the maximum power will be delivered to the load for the condition when maximum power is differentiate with respect to load resistance RL, that will be equals to 0, that is dP by dRL equals to 0. So differentiate power P, that is VTH square divided by R plus RL square plus X square into RL with respect to RL. So now we are doing differentiation, that is this is U by V, whereas U is VTH square into RL, V is the denominator term. So this is given by V into du by dt, whereas V is R plus RL square, RL whole square plus X square as it is. VTH square RL with respect to RL is nothing but 1 minus U into dV by dt. U is VTH square into RL as it is. Here x with respect to RL will be 0. R plus RL whole square with respect to R L, you'll get 2 into R plus RL equals to 0. Denominator will be whole square, you will be sending that to the right side, it will be also 0. So now VTH square you are taking common. By taking this VTH square common, so the rest of the terminal is R plus RL whole square plus x square minus 2RL into R plus RL equals to 0. Then you are sending this VTH to right side, that will be 0. Rest of the thing is R plus RL whole square plus x square minus 2RL into R plus RL equals to 0. Simplifying this, so a plus b whole square, R square plus RL square plus 2R into RL plus x square as it is. You are open the bracket, 2 into R into RL, 2 into R into RL plus 2 into R plus into minus minus 2 into RL square, 2 into RL square. So plus 2R into RL minus 2R into RL will get cancelled. So R square as it is and plus RL square minus 2RL square, you will get minus RL square plus x square as it is. Therefore, you are writing RL square, you are sending this to right side, RL square equals R square plus x square. If you are writing RL, square root of R square plus x square, whereas RL, this square root of R square plus x square is nothing but impedance, that is a magnitude of impedance, therefore RL equals to Z. So if x equals to 0, when you know the value of Z as R plus jx, therefore if the x is 0 means Z equals to R, that is nothing but load resistance is same as source resistance R or else R. This is the derivation of maximum power transfer theorem when load resistance is same as source resistance. Similarly, if the load resistance is fixed but the load resistance is variable, if it is a AC circuit, for the same circuit R plus jx, I am writing that as a Z now, and the load is ZL. So this ZL is given by RL plus jXL VTH. So ZL is RL plus jXL, where RL is the load resistance and it is fixed. XL is the load reactance, it is a variable, so that the total impedance is Z plus ZL. And you know the Z R plus jx, ZL is RL plus jXL. So R plus jx plus RL plus jXL. So you are rewriting the real terms and imaginary term, R plus RL plus J you are taking common in the bracket x plus XL. So the total power current which is given by now again VTH divided by Z plus ZL. So I is given by voltage divided by equivalent impedance, that is Z plus ZL. You know Z plus ZL now, therefore VTH divided by R plus RL plus J into x plus XL. You are writing the magnitude of current, so that square root of VTH square divided by R plus R square, RL square plus x plus XL square. Square root and square will get cancelled, so that VTH divided by square root of R plus RL square plus x plus XL square. You are removing the complex conjugate Z, sorry, you are removing the Z operator. Then you are defining the power delivered to the load, that is I square into RL. So I, you know, I square is nothing but VTH square. In the denominator, square root and square will get cancelled. You can get R plus RL whole square plus x plus XL whole square into RL. So again, to get the maximum power for AC circuit, again dP, now in the previous case dP divided by DRL. For here, because the resistance is fixed, impedance is 0. Here you are considering the impedance, therefore dP divided by XL equals to 0. You are differentiating the whole term with respect to XL now. Again you are using the U by V rule, so that V into du by dt, V you will be writing as it is, into du by dt differentiating this term with respect to XL, that is 0 minus u into, that is nothing but VTH square into RL into this dV by dt, differentiating this term with respect to x, so this will be 0, so 2 into x plus XL, that will be equals to 0. Then you are sending the 0 into this term will be 0 only. Then you can read it as VTH square minus VTH square RL into 2 into x plus XL equals to 0. And you are sending this to right side, that becomes 0. You will get 2x plus 2 also you can send if you want, or else 2x plus 2XL equals to 0. Therefore, you are taking common as a 2, sending right side, that will be 0. It is nothing but load reactance is the complex conjugate of equivalent reactance. So that for AC circuit, ZL equals complex conjugate of equivalent impedance. For DC circuit, load resistance equals source resistance. If they asked you to derive only when the load resistance is the same as source resistance, means you have to do it for only first case, that is still here you have to do the derivation. So thank you so much. If you like this video, do subscribe and have a nice day. Thank you.